Let's look at a few tricky and somewhat unexpected antiderivatives. So, a not tricky, comparatively, a not tricky I can't spell tricky. Okay, a not tricky antiderivative in comparison would be if, let's say, f prime of x, we have a mystery function little f, and our derivative is known to be, let's say, 5 x to the 4/3. This isn't the easiest antiderivative to do, but it's not too bad. F of x equals, well, it's a power. So what do? When we differentiate a power, we subtract one. So when we antidifferentiate, we're going to add one because we're trying to find the mystery function that when we differentiate it, we'll get x to the 4/3. Let's not worry about the 5 for a second. So we're going to get x to the 7/3. Now would that work? Well, that wouldn't work definitely because we get 7/3 times x to the 4/3. But hey, we're close. We got the main part. We just have to kill off that 7/3. We just take 1 over 7/3. It's going to be 3/7 when we simplify it. But that's going to kill it off. And so we've added 1 to the power, and then we divide by what we just wrote in the power. Okay. But then, does that give us the 5? No, but we can just put the 5 in. Because constants are so simple for derivatives, they're simple for antiderivatives as well. Constants and sums are simple for antiderivatives. Now, one thing, plus c. Always plus c. Unless we have some information to determine it, we're going to have that plus c. Okay. So the simplified version would be 15/7 x to the 7/3 plus c. Okay. So I do that not because it's the main point of this video, but for comparison. You just add 1. Let's just write down the general rule that we've used there. If f prime of x is x to the n, then f of x is going to be, you take x, let's put it in front. You take x to the n plus 1, you add 1 to the power, but then you divide by n plus 1, and then you add c. Okay, this is definitely in the book, but it's good to review. Okay, now, here's the first tricky one. When would this process not work? It's very general. It worked for, I purposely did a fraction here to illustrate that it doesn't just work for integers, but there's one number where we couldn't even write this down and make any sense of it. Think about it for a second. And that would be where n equals -1. Okay. We're totally stuck if n equals -1 according to this idea. And the key, as with all of this, well, what was the key here? The key was that we knew a derivative fact, and we took an antiderivative fact out of that. We just look further in our table, our knowledge of derivatives. And we look for a derivative that's equal to 1 over x. And guess what? We have one. Okay? It's not algebra, though. It's f of x equals ln x. Then f prime of x equals 1 over x. Okay, so that's the first tricky thing, is that it's just not a power. It's a new function. And this is a really, really interesting thing. And in fact, some people use it as the definition of the natural log, as the antiderivative, or one antiderivative of 1 over x. Because this is so cool that just simply asking for the antiderivative pops you out of algebraic thinking into ln's, which is really a higher order of thing. Okay, now, but that's only the first tricky bit with ln. Here's the second tricky bit. Let me actually go ahead and graph that function, ln x. There's a real problem with that, which is that it only exists for positive x values. Let me force this thing to actually give us some negative values. And half the graph is empty, because you can't take ln of a negative number. But let's see. Let me graph on the same graph 1 over x. That has no problem existing for negative values. So over here, it's true that the derivative of this, sloping steeply upward then not so steeply upward, is this function. Big positive values, smaller positive values, but still positive always. But there doesn't seem to be anything corresponding over here. That was not a big issue when we were taking derivatives, because you just take ln and you say its derivative is 1 over x, and you don't worry about this extra stuff. But now, I want the antiderivative of this function, and I'd like it to exist wherever 1 over x does. So I need a new thing over here. Well, it should be very similar to ln x, because this guy is just a copy of this guy shifted, flipped through the origin. 1 over x is an odd function. And so I would want to get something that looks very similar to the ln x curve. It's just going down not very steeply, and then very steeply, and then steeper and steeper and steeper to mimic these guys, which are negative values and then more and more and more negative values. So in other words, I want the flipped version across the y-axis of ln x. And we know how to do that. We know that if we plot, add one more item, ln of minus x, then that will be exactly what we want. Aha! So now here's a function that has the right profile to have the derivative be this part of 1 over x. So if I wanted a really clunky answer, what I could say is it's ln x if x is greater than 0, or ln of minus x if x is less than 0. But that sounds familiar. What is a function that is x if x is greater than 0 minus x if x is less than 0? It's just absolute value. And so it's actually ln of absolute value of x. Let's check that. Let's delete this guy and delete this guy and add back in ln of absolute value of x. No change. That's exactly what we wanted. Okay. So it's really this guy that is the antiderivative. So two subtle things. It's not a power at all, which you might guess from the other powers, and you get this absolute value. And of course, you also need the plus c. Because graphically, geometrically, we could lift this ln function up, and it would still have the same slopes and still have the derivative be 1 over x, which is these guys. Okay, so that's the real honest-to-God antiderivative. Notice it still is nasty at 0, but that's okay, because 1 over x was nasty at 0 anyway, so everything is nasty at 0 in this kind of problem. So one thing that I've noticed that I want to highlight is we are not redefining the natural log. And in particular, if the reason you've got a natural log in your problem is that you're solving an exponential equation, like you started with y equals e to the x, and you rewrote that as ln y equals x, this doesn't change to an absolute value. If the ln is coming into your problem because of exponentials, it's still ln, no absolute value, and we'll still see that in our problems. But if it's coming in as the antiderivative of 1 over x, you need this absolute value. And you're actually going to be doing a problem, well, if you're in my class, that involves negative values of x, where this is absolutely crucial. Okay. Now, here's another one. Tricky one. Okay. And again, let me, to illustrate what's going on, to emphasize, everything we know about antiderivatives so far is just based on looking up what we already know about derivatives. It's not about manipulating. We didn't rederive this result here for powers. We just remembered it and kind of rephrased it. We didn't rederive the fact that derivative ln x was 1 over x. We already knew it, and we just had to remember it and look it up. But we had to go further, look further in the table. Okay. So if you want to stop the video right now, it's a good idea, because I'm going to ask you if f prime of x is 1 over 1 plus x squared. What's the antiderivative? What is f of x, the mystery f of x? And I claim you can do this problem very easily if you have any calculus book and you just look at a table of derivatives. You will see this as the derivative, as the answer for a previous question. Now it becomes the question, what's the corresponding answer? And if you look carefully at a table of derivatives, we actually have seen this, but again, it was in a surprising place. It turned out that the derivative of the inverse tangent function had nothing to do with calculus. When you took the derivative of this guy, suddenly, it had nothing to do with trigonometry, rather. Somehow the derivative doesn't even understand about trig, somehow, or maybe it secretly does. The derivative of inverse tangent was 1 over 1 plus x squared, so the antiderivative of this guy is inverse tangent of x and, of course, plus c. Okay? So in particular, it is absolutely not equal to ln of 1 plus x squared. You might have thought, oh, okay, yeah, this is natural coming from the ln. He's going to say it's ln of 1 plus x squared. It's just not true. And that's another thing that's very important about antiderivatives, and it really comes from the derivative information. Let's see why this isn't true. The derivative of ln of 1 plus x squared, you are going to get a 1 over 1 plus x squared, but you're going to get the chain rule as well. This is going to be times 2x. Okay, so maybe I can fix that. What's d by dx? What if I just divide by, take this and just divide by 2x? What rule do you have to use now? Think about that for a second. What rule do I have to use? What's the outer layer of this function? It's the quotient rule. And the chain rule. And. It's not going to work. It's going to be a mess. And in fact, we know it can't possibly work because we already know a function. And we in fact know all functions whose derivative is 1 over n plus x squared. It's not anything to do with algebra. There's no algebra you could possibly write down that gives this answer as a derivative. It has to involve trig. And that's what makes it really tricky. There's other examples, but I don't want to give them away.